Can you hear me now? Okay. So hi everyone. I wanted to give a talk that's basically based around the chapter actually that is in a book that Paul edited with Angel Mahoney that was put out on next generation computational social science, essentially, in that topic. What's the exact title of the book, Paul?
Social behavioral modeling for complex systems.
Right. So if you're interested in these topics in general, I highly recommend the book. It came out of a workshop that Paul organized at RAND, but then involved contributors beyond just that workshop who are interested in this kind of topic. And this was kind of where I started thinking. So to give you a little background, right, I spent a lot of time doing agent-based modeling for a long time. And then I went to a business school, and I was still doing agent-based modeling in that business school. But then I realized that there were all these machine learning problems that business school people wrestled with that they didn't really know how to handle, right? And so I started doing a lot of machine learning again, right? Even basic stuff from everything from decision trees to random forests to neural nets to deep learning approaches, right, that they weren't able to do. And then I got to a point a couple of years ago where I said, well, why can't I combine these two interests? Why can't I combine this interest in kind of machine learning, big data analysis with agent-based modeling? And I think in many ways, inverse generative social science is really taking advantage of that, right? The fact that we now have these large-scale micro-level data patterns that exist that we can run machine learning algorithms on to discover patterns in that data and then use those patterns to influence the agent-based models that we're creating in many ways. And so that's kind of my particular spin on this. I'm not sure that's everyone's spin on it, but that's my take on it. And I feel like we actually have a little bit of an obligation, right, from a social science perspective to really start to push this kind of a perspective. And really what I'm going to and this is not in the chapter, but this is kind of something I want to get to now. I feel like we need to combat a lot of the efforts that are being made to look at this big data for social science in ways that I feel are, quite frankly, unethical at the extremes, right? Let me talk through that. And so the beauty of big data, you all know it, right? Individuals are leaving their literal fingerprints at times in these big data traces of efforts that we're getting. I remember I was at a meeting actually at MITRE when Rob referred to this as digital exhaust. I think you were referencing Duncan Watts, right? But it still provides us with this indication of what people are doing as they move around the world, right? It might be digital exhaust, but it's digital exhaust that indicates, where they are and what they've been doing and things like that, and so can provide patterns that we can look at. There might very well be other data sets out there that could be better for certain questions, so this is not applicable for everything, but I think in some cases it does provide us interesting actions, right? And, especially in my realm that I spend a lot of time in, which is diffusion of information, social media marketing, right? There's a lot of data out there in that space, and literally that exhaust and what's happening in that exhaust, it has become almost as valuable as what's actually happening in the real world, right? And so just understanding that exhaust is a problem and an interesting problem in and of itself, right? The lure of big data, right, is that we have our data, we build a model, and we get some output, and that presents us with insight into the way the world works, right? So, and there's been these papers that have been written in computer science a couple of times. They're good data, more data beats better models every time, right, and things like this over the years, right, that basically try and argue that we're beyond the need for theory anymore, right, that we can just build these models and make predictions and we can go on with our lives. And there's been a lot of combat even within the CS literature against that. That's not a widely accepted belief, right, but people have made this argument, right? And so who needs theory anymore? And I'm gonna give you 3 quick vignettes as to why we need theory, right? The first one is the Google flu trends example. So many of you may have heard this, but Google built this tool a while ago called Google Flu Trends, which did extremely well. So up here we have the orange line is Google Flu, the blue line is the CDC, and then the the hyper blue line, I think, is the lag CDC, the actual results, right, that the CDC found. And for the first, 2 and maybe 2.5 years, it's doing really well at making predictions, right? And then all of a sudden, Google Flu Trends starts wildly over-predicting the amount of flu. And then it predicted under. I think if you go beyond this and extend this line out, it starts under-predicting and over-predicting, and it's very disconnected from the data, right? And they did this, and so they did this using a straight kind of machine learning approach of just finding as many correlations between searches on Google and the flu patterns that they could possibly have. And they did some really good stuff, like exclude seasonal things. Like they took out words related to sports, right? Because those would kind of put seasonal aspects into it that they didn't want, right? And they did a bunch of other exclusions along that to try and make the model better, but still it had this problem, right? And there's a whole discussion as to why it failed, right? And especially given the fact that it did well. Part of me thinks it might purely be a case of spurious correlation, right? We know, like, and by the way, there's a great website called Spurious Correlation that I highly recommend you take a look at. One of my favorite stats from it is that from 1999 to 2009, the divorce rate in Maine was correlated at a 0.999 level with the purchase of margarine in the U.S., right? The national purchase of margarine, right? So if you think that just if you ever thought that correlation was equal to causation, go to this website and you'll be disavowed of that notion in an instant, right? But what's the problem with this? The problem with this is we don't know why Google Flu Trends failed, right? Because of the fact that we don't have a theory to explain why those particular search terms that it had discovered would be related to actual flu incidents, right? We don't have any way to now take the data, the model that was built by Google, and go back and figure out where it went wrong, right? Another, and this kind of gets to some of the more harmful potentially examples, but and by the way, this example is, and the next one, I think the next one is also mentioned. And Kathy O'Neill has a great book called Weapons of Math Destruction that I highly recommend you take a look at. That's about how algorithms and big data are destroying society, right, essentially. And so I highly recommend you take a look at it. This is data, so what this is data from, this is the New York City public school system created a way to evaluate how much a teacher added to the schooling experience, right? And they did this in a really nice way. They basically, took measurements of how well students did on tests before they entered that teacher's class, how well they did at the end of the year. They made predictions based upon that student's past experience as to how well they would improve, right, what the expected level of improvement on those tests was. And then they measured how much the student was above or below that prediction, right? And if they're above that prediction, the teacher gets more points. If they're below that prediction, the teacher gets worse points, right? What they failed to take into account for was the fact that teachers might start manipulating these tests and start manipulating the way students answer this test, and might, since they know they're being graded for performance on this, even in the worst cases, give out the answers to these tests before the students take the tests, right? And so as a result, it might very well be the case that a teacher looks like they're doing really well, but all they're really doing is spoon-feeding the kids the answers. So and this is actually done by a middle school math teacher, I think correctly, right? One teacher said, well, I could get all of these scores. So they took all the scores for teacher improvement, and they found a set of those people, a set of those scores for those teachers who taught the same teacher, who were the same teacher, right, teaching the same subject, right, in the same grade level, right, with students who had the same pretest score on, right, but were teaching in 2 different classroom settings, right? So they might be teaching in 2 different, New York public schools are such that they might be teaching in 2 different physical school buildings. They might be teaching the same class in the same school building, whatever, right? They're teaching the same, but they're teaching the exact same thing. So if this teacher score tells you something useful about that, then as soon as we plot, those 2008 to 2009 ranks, it should be somewhat linear, right? But instead, it's a complete uniform mess, right? And, again, in this case, maybe they have this theory, but they're also throwing in a bunch of additional variables as to what's going on in the system that they won't reveal to us and they won't tell us what they're doing, right? In fact, this data is almost impossible to get now because the New York City school system has just clamped down and said we're just going to use it and go forward with it, right? But the truth of the matter is that this is another reason why we need to make sure that there are theories and systems underpinning the relationship between our data and our results, right? One last example, this is predpol. And so predpol is a tool that's being used by police agencies to predict where crime is going to happen before it happens, right? The problem is, as Kathy O'Neill really puts it well on this one, we have really good data about where where arrests are made. We have very bad data about where crime actually occurs, right? So this algorithm is based instead not on where crime is occurring, but based upon where arrests have been made. Historically, the police system in the United States has been extremely racist, right? And so as a result, there are a lot more arrests in black neighborhoods than there are in predominantly white neighborhoods, right? And so because of this, the predpol system, which learns from the historical data, even though it doesn't take race into account, predicts that crime is going to happen in black neighborhoods more often than not. Now, one particular example of where we do have good data about crime is on illegal drug use. There's been a comprehensive set of studies about who smokes marijuana, who takes drugs of various kinds, and that has been done again and again and again. And we have fairly good data about this, right? And they did a study in Oakland, which, of course, now what's interesting is that marijuana is now going to recreationally legal in California, so this may not apply, but at the time it applied, right? And we knew that the estimated drug use in white predominant neighborhoods is actually higher in Oakland, California than it was in predominant black neighborhoods and predominant other neighborhoods, right? But where did predpol, they got predpol data for the same exact city, same exact system, and where does predpol predict that there will be drug incidents, drug arrests, drug crime? Of course, it's predominantly black neighborhoods, right? And why is, well, first of all, this again is a black box method, right? We don't know exactly what predpol uses to make predictions. We've guessed based upon these various things as to how it makes these predictions, right? But we don't know for sure. And I think that that's also a good argument. That's another argument as to why we cannot allow these black box methods of analyzing data to make predictions to be the future of social science, right? We need to draw theories instead. If we had a theory explaining this relationship, and as we expect it's related to past historically biased data, right, then we can say, no, you can't use that data, right? There's another great example I remember recently where someone was using, I think this was maybe even also in the crime prediction space, where they said, oh, we don't use racial data, we just use zip code. But in the United States, zip code is almost a perfect proxy for socioeconomic status and race in many cases, right? And so it's one of these examples where we have an obligation, I would argue, as social sciences to avoid what I was trying to figure out what to call this, and in the end I called it the Florence whale effect of black box modeling. So many of you may not know the story, but I wanted to use it because it's a great example of one of the first viral videos on the web. So, and I highly recommend you Google Florence whale explosion at some point in the near future. But there was a dead whale on the coast of Oregon, right? And in Florence, Oregon, right? And the decision was made by the Oregon Highway Patrol that they needed to remove this whale because it was stinking up the entire space. And it was making it very unappetizing to come to this beach that they were trying to promote, right? And so the decision was made to place a large amount of dynamite under the whale in order to blow the whale out to sea, right? So their solution, I would argue, much like black box machine learning approaches, was to just take the biggest possible hammer and throw it at the thing, right? So they placed the dynamite under the whale, right? Exploded the whale, stood about a half mile back, and if you watch the video, there's people applauding as the explosion goes off. Those applauds shortly turns to shrieks of panic as huge chunks of whales start falling down on them because they were not far enough away. In fact, one piece of blubber flattened an entire car that you can see in the video. So, I mean, it's essentially the argument of unintended consequences, but I feel this gives it a more humorous name, maybe too humorous at times. But, black box data models exacerbate, I would say, in many cases, the very problems they are trying to solve, right? Or have huge unintended consequences beyond what they're trying to solve originally. And without a theoretical tie between the models and the data, it's really hard to figure out why they're failing and to figure out what's causing the unintended consequences. Take care, Josh.
Thank you all very much. I'm delighted at the proceedings and looking forward to moving forward.
Yeah.
Thank you very much. Sorry again.
Yeah. Okay.
Hey.
So we have many examples that I've shown you of places where this has been proven right, that these big black box models have failed. And in fact, I would argue that there's probably many, many, many more out there that we don't know about, because a lot of times the unintended consequences that they have are the same disadvantaged people who don't have the voice in these kinds of meetings to really express what's going on with these problems, right? And so I would say, I really want to put the onus that we have a societal obligation to move towards these inverse generative approaches, among others, which provide us a link between these, right? And so in the chapter, yeah.
Okay, just to interject on that a little bit, because I think that there's a valid critique and I buy it and everything.
Yeah.
But it also strikes that if in fact I'm one of the black box model builders and I hear your critique.
Yeah.
My incentives are clear. I'm just going to try to make the black box line up, and then I think you're still unhappy though.
Yeah.
But I think you don't want to tie the critique to merely the performance. You want to tie the critique to the fact that it's conceptually what we want.
Right. So that's what I was trying to say, and I may not have said it very well there, right? It's the fact that these unintended consequences, like we can put in, racial disparity as an output, right, of our system. We can put in but there's always going to be something that we don't know about, that we don't understand, that we can't put in there, right? And so if we're in the black box world, right, it's really hard to articulate what all those things might be. What? I still can't hear you, sorry. A link space.
Latent variable.
Oh, latent variable model, right. But we still don't know what all those latent variables are, right, would be my argument, right? No, we don't, right? But if we start with theoretical principles first about what the relationship might be and explain those, right? I mean, eventually, if you add enough latent variables, right, I would argue that you've gotten to a non-black box model to a large extent, right? If you're like, I have a latent variable that proxies for race, and I have a latent variable that proxies for, I mean, at some point, what's the difference?
I think you're playing in the space of mechanistic model versus non-mechanistic
model. Yeah.
And you're also playing in the space of explainable deep learning models.
Right.
There will be explainable deep learning models where they're going to take these black boxes and they're going to be able to actually run things on and tell you what they say.
And honestly, I've yet to see an explainable deep learning model that works really well for something other than images, right?
That's because you're not touching causality either.
Yeah. But
you're talking about causality, you're talking correlation, and
you're right. I am sweeping over the 50. Like I could stand up here talking about all the individual reasons why I see this problem, right? And I think it's more compelling in many cases to present a couple of examples of where they failed. Maybe in a longer treatise, I would tie them back down to what's the reason why each of the, because you're right. I mean, for instance, the the Google flu model, the problems with that are very different, I think, than the problems with Predpol or something like that, right? And there's probably different epistemic reasons why they're different, why they're failing, right? I totally agree with you. I guess I'm just trying to say there's a whole heap of problems with approaches that ignore theory, right? And we have an obligation to not use those approaches for a variety of reasons. And you're right. It's a totally fair criticism. I could be more articulate about what those reasons are. Yeah.
Just, I really agree very strongly. And one of the reasons is I've spent a lot of time on policy problems over the years. And to give you a little anecdote that actually affected discussions in high places, when we're in the counterterrorism business, social scientists were asked, and they came out with published papers by very big name people, and it showed that there was a correlation between terrorism and democracy. Oh, and there was a correlation between terrorism and development. Golly. Well, any fool, as a policymaker, knows this is not very useful to him, right? Because the implications are you stop this democracy crap and you stop development and it distracts. Well, that's wrong. So the thing I would say a little differently, and I want to go back to the Schelling thing also. If one only read the Schelling article and you tried to draw conclusions for policy, you would conclude it's hopeless because even a little tiny preference, which is natural, leads to total segregation. So forget the whole business about integration and so forth. It's hopeless. So the thing that I would add to what you're talking about is that you have to have a model, you have to have theory in order to discuss and also argue about what the implications should be.
Yeah. I think that's
the data.
Yeah.
And people
that's a good way of phrasing it.
All the time wrong. Yeah. And I'm much more sensitive to this probably than many of you are, but I think that statistical fits are, in my experience, more often counterproductive to policy discussion than not. That's a pretty strong statement. Now, if we were talking about economics, where you're talking about marginal effects, there I could argue the contrary, because on the margin, it's, that's a really well-developed field that works. But in most areas, the correlations are worse than not having.
Yeah, I think that's a great way to articulate it, as being able to explain all those linkages is very important, right, in many cases. Yeah.
So I like these ideas, but it's not even just the black box part. So one of your examples for Predpol is they were just training to the wrong cost function.
Right.
And you can tell what they're training to.
Right. I mean, yeah, we think we know, right? I mean, there might be other stuff in there that we have no idea what it is, right? But we think we know, right? And that's part of the argument as to why I would make it, right? Like, if like, the criticism of it can be much more clean if they told us, right, it's exactly based upon these arrest record data, right? But the fact that it's not clean in that, right, gives them this ability to kind of argue back and forth. And in fact, ProPublica did a whole deep dive on this where they tried to figure out what the algorithm was and go beyond just those details.
If you had a theory that said these are the relevant variables, that would, you're allowed to play around with these.
Yeah.
This is what you're trying to optimize.
Right.
And then if they came back to you with an explainable AI model that said, it just so happened we threw in zip code and it was so much better that we liked it a lot. You've got a theory for why it worked. At that point, you have to say, no, that's not allowed.
Yeah. Yeah, I mean, I do think that there's something about this articulation between what are the variables that are going into the system and what are coming out of it, and trying to show what the relationship is there, that I think is the critical aspect. Yeah, Anna May.
So I think it is features, but some of the stuff I see here, as a computer scientist, like when you do terms, I go back to stuff like simple grounding problems, which is called anything. This means this is the social norm, or this is my likelihood that I'm going to cooperate with you.
Yeah.
But that's still a grounding conversation. And grab a number, right? As you just make that qualitative things, but numbers
But I think that at least, I mean, I would,
I mean, it's a little bit squishy.
I mean, I would argue that you're totally right, and it could encompass many different things, but like, and there is a lot of power that we have, and I think that,
Very emotional ones.
yeah, I mean, I actually wonder, like, I think this is somewhat of a separate conversation from this workshop, but I do believe that there's been a push for like a data science code of ethics, right, for instance, and I believe that there should be, you know, a social science data science code of ethics, right, that's somewhat related. It might be.
I think that already happened. No, I think, yeah, this is a sense of lack of ethics and morals underpinning some of the computer science work. We're all just ripping on cool things we could do with our computers. But
Yeah.
I think that there's a longer history and a deeper field of study in social science that
Right.
has created many more ethics and
There's a lot to be said for that, yeah.
resolutions and concepts of ethics and morals that you
Yeah.
can see with.
Yeah.
So,
Yeah,
we're even using IRBs.
I,
Like that, the Cornell study that was looking at manipulating the Facebook.
Facebook data, yeah,
Right? They didn't have an IRB.
yeah.
They were computer scientists, I guess, and they didn't. There's some out there who just don't know you need IRBs.
Yeah, yeah, yeah.
But I just would counter that with like, it gives me confidence in a way that sometimes someone building me a model that tells me about emotions and numbers on emotions doesn't.
Yeah, I mean, well, I think one of the goals of this workshop, maybe this does tie back in, right, among other things, is that critique has been leveled for a long time against the pure, and I guess Josh and Rob could speak, against the pure generative social science approach, right, which is, I'm going to make a theory, run that theory, and show you some insights, and I'm never going to tie it to data, right? I mean, the Schelling model, it's a powerful model, but there is no tie to data, right, except for these stylized facts that we observe about it, right? And so I think part of the goal of this approach, among others, is to find ways to actually tie those more concretely to data.
Part of the issue is that, you know, the second bullet on here, which is that there are issues with social theory that social theorists discuss. So the whole, field.
I leveled the full articulation critiques both ways.
The whole field of critical realism is, you know, attacked on the basis that you're talking about unobservable powers of unobservable objects, and building a theory around that. Yeah, you've got these symbols and you're interpreting them, but what can you really do with that?
Right.
Yeah.
Actually, another way to look at this is that we're criticizing the machine learning and statistical models here for not being able to recover from our own bias in the way that we set them up. Right? In the predpol example, a big piece of it is the biased data that goes into it.
Right.
And so I'm wondering, maybe I'm helping you get to your next slide here, but if we're saying that the answer is to move from the data back to the theory, then what are we doing to address the fact that all of the problems in the data may have come from our own human bias in the first place, and why could we expect that not to be implicit in the theories that we create?
So there's exactly a paper that I've wanted to write for a while. So we do have experience in social science. I haven't written this. I didn't put the slide in. I should have put it in, right? Which is essentially trying to cover all of the ways that bias, not in the computer science sense, but in terms of the social science sense, can actually enter the system, right? And that one of those is in, you know, the way historical data has been collected. And that's something that we've known from social science for a long time, right? There is a classification of these different types of bias that we can put in there, and we can start to label those. And I think having that device, which is not what this talk is going to be about, right, but could become what this talk is about, right, would be very useful, right? Because then as a big data social science modeler, I can go down my checklist and be like, are there any concerns with any of these biases that I have? It's not going to be perfect, right? You might still ignore the fact that it turns out that a bunch of cops in Oakland are racist, right? Like, you might just not be aware of that, right? But at least, you know, having that checklist will help you start to articulate that.
The example that you missed that the computer scientists got wrong, again, another one similar to this, is that they were doing all the vision, a lot of the face recognition and face generation. Actually, I think it was more recognition, was being trained on white people. So black people were being mistaken for being gorillas.
Well, and in fact, if you want a whole book on just...
They had a poorly biased data set, and in fact, I think IBM and Microsoft, the two data sets that sort of are the basis for all the great results in deep learning in vision, have been withdrawn.
By the way, another example of that that's along those lines, and I highly recommend, I can't remember her first name, Perez, has this book, Invisible Women, that is about the fact that there's this huge data gap with women, right? So here's a quick test. If everyone goes home and talks to their smart device, right, it is 90% more likely to recognize a male voice than it is a female voice, right? And if a female voice talks with a deeper tone, it is more likely to recognize them, right? And that's because those same exact data samples that we trained all these machine learning tools on, the audio samples that we have are something like 80% male, right? And so as a result, we have huge errors, huge data gaps when it comes to male versus female data in this space as well.
Again, so really hard. It's like Tim Berners-Lee, so the inventor of the internet and HTML, really, and, the web. He thought he was basically giving everyone the democratic access to equality, and it's been turned on its head. And like, if you ask him, he's like, "Oh God, what a mess!" But could you have modeled ahead of time what was going to happen?
Yeah. It's a tough one. Yeah.
All those scientists predicted this.
Yeah, predpol is actually a very, very interesting example because I would argue it's a failure to look beneath the data to dynamic structural systems. The actual answer for why the discrepancy, predpol is actually correct if you understand the motivation factors and the signals that are available. There is a structural difference in how drug dealing is done in black communities versus white communities. In black communities, it's much more likely to be done out on the street as opposed to private transactions in the white community. So therefore, there's a lot more community complaints about drug dealing in black communities, and police are always trying to minimize citizen complaints. Second, think about it for a second, it's way easier to arrest a drug dealer who's selling drugs on a street corner than it is to arrest a drug dealer who is selling by private appointment in his apartment. So if you model the system with those two structural factors built in, you'll actually get a result like
Well, I mean, if your goal is to arrest black people, then yes, right? That's what you'll do.
Let's say your goal is to minimize citizen complaints and to optimize the use of your police force to do so.
No, but there's other solutions, but that's because of traditional methods by which we use police, right? That's not because of anything to do with actually reducing crime. That's because historically we've gone out and arrested the people who are most easily available to arrest, which is black people.
Cool.
So if your goal is to arrest black people, then that is what you will do, right?
I think you got it backwards. Their goal is to arrest people who are easy to arrest, who happen to be people who sell drugs on street corners.
Right, so you're arresting people who are easy to arrest, happens to be low-income people who don't have a lot of money, who are doing drug deals on the streets. You're right, so, and those people are historically black.
I was not going to mention this, Bill.
It has nothing to do with their blackness. It has to do with
exactly. It has to do with their black, because structurally in the United States, black people make a lot less money than white people.
I think your predpol example is actually not a great one for what you want to do with it here, because it turns out that predpol is based on the community of people associated with the Journal of Quantitative Criminology, and there are mechanisms in there. Well, whatever political founder. The real trouble is, I think you've hit it, but I think it's more than half of the problem that you're articulating here is that it's the black box part of it. That's the pathology. It's not open source because predpol is in fact a mechanism-based system. It's not just a correlation system. It actually does. This is Brantingham at UCLA, George Tita at UCI. I mean, these are all serious criminologists who who write down mechanisms for where crime happens as a result of, and then where are the perps going to be to get arrested. I mean, so there is in fact this underlying mechanism in there, but the real pathology is that we can't see it, and so there's no way to, whatever the implicit ethics are of the model or of using it, it's opaque.
So once you tell me what the model is, I can reject it, but I can't really reject it when I don't know what it is.
Right. I very much agree. The way I was using the black versus white example was as kind of a synecdoche, right? It's standing in for the other problems that exist in this system, right? There might be a whole host of other problems that we don't understand as a society because it is a black box approach, right?
But I think because it's a closed approach.
Yeah.
Well, I don't know if that's where you're going, Bill, but there is a whole...
I'm not going anywhere near
There is a whole movement of open algorithms, right? So there's this recognition that algorithms have so much power on society, being search algorithms, being, predpoll. Whatever an algorithm has power to rule the way you live and you interact in a society, you should have access not only to see the algorithm, but also to, in some way, influence what algorithm should be the right, because it's almost like an implicit law. You're making laws without people.
Yeah, and that's a lot of it. That was not the line I was hoping to go down today, but that's exactly what Kathy O'Neill's book is all about. Yeah. And so I won't spend a too much. I don't feel like I need to reinvent that. That's exactly what her book's about. And I mean, to get back to Jim's point, I think that this is arguing that you're right. Under the current policing system, this is probably appropriate. This is arguing that this is the use of data models to show that there is something inherently flawed in the current policing system, right? It's, again, the synecdoche argument. It's the small piece of what predpoll is doing standing in for the whole of all the systemic problems that are getting out there. And I think that as social scientists, that's an obligation we have, right, to try and identify these aspects of things where one aspect stands for the whole, right, where one problem or set of data problems that we can find we can say, because we found this pattern, there's a good reason to believe that those patterns might exist in many other ways, and we can start to articulate theories, which is really what I'm getting at, to try and explain.
We actually can't do it, though, if we can't see the model.
Yeah, I totally agree. Yeah.
I mean, the example that Blake knows about more than anybody probably is that, when correlations first became used in mortgages, bankers correlated on rates, right? Mm-hmm. And then Congress passed a law that you cannot do that.
The models, the eligibility for mortgage models cannot correlate on rates. Mm-hmm. What do we have today? Now we have big data models,
right? Which go around it
and get the same
answer.
But we don't. But Congress can't open up the black box and say,
yeah,
here's how it's doing that.
But here, let me take this back to where I actually wanted to go with this talk, right? Which is that I don't want. Yeah, I do feel like we have an obligation also to fight against the big systemic use of these models in those kinds of spaces. But even if we, eating our own dog food, right, even if we're just looking at what social science academics provide about social science research, what I'm arguing is that we have an obligation to fight against the use of black box models in our own fields, right? And there is a growing tendency to apply those models in ways that are non-mechanistic, right? That don't provide the mechanisms linking the inputs to the outputs in many ways. That's the fundamental thesis I'm going for, right? Not really. I kind of like drawing on these examples from big societal spaces because I find them interesting and show how what the big ramifications are if we continue to perpetuate some of the use of these, right? But I really am just arguing the small argument right now, which is that in our own field, we have an obligation to move away from these.
I just wanted to add a quick thing is that these things should go interchangeably, and both ideas
I'll move to the next slide while you're
talking. Need to talk to each other because, for example, I work a lot with psychiatrists, and they really want to see black box models, and the reason is that, I was like, well, why do I, can you tell me more about the story behind it? It's like, no, we just really want to give you the data and want you to do something with it, and we really don't want you to know anything about what's behind this data. And so the logic turns out to be very interesting. They say, well, we do have all these theories and explanations, and with these theories, you can only go this far. And we can predict, I don't know, say, 65% accuracy roughly. So now we want you to use all the black box tools to see if you can predict that. So if your black box will give you, 90% accuracy versus 70% accuracy, well, it means that maybe we'll need to start looking into what could be new theories or why things go that. What is that we're missing? Yeah. But if our theory-based model gives you 70% and you throw in your best black box and it gives you like 72%.
Yeah.
It means that, okay, we have exhausted ourselves, like we cannot do better. There is no reason to develop more theories or explanation. So I think it's all needs to start with a question of why.
I agree with you. And I was just trying to figure out if like maybe there is an addendum to be made here, which is that when I say that all social science models using big data should be interpretable from a theoretical perspective, I mean that in terms of adding to scientific knowledge or adding to the truth we know about the world, in whichever case you want to put it, little t-truth, right? I don't mean it in terms of data exploration, right? Like if I just want to explore some data and show some relationships and just play around with it, that's fine. I can look for those relationships. I can look for the fact that, you know, zip code and race are highly correlated, right? And there's nothing wrong with doing those kinds of things, right? Just making that statement, right? Now, if I'm trying to argue that one of those things causes the other thing, is there is a scientific evidence that these two things are interestingly related in some way. I have trouble with the word causal because of the fact that there's so many different definitions of it right now. But like, you know, then I don't feel like what I'm saying is we should not be publishing papers along those lines, right? That we should not be publishing papers that say, you know, I have a model of how your brain works, and I can make a 90% accurate prediction, and I can't tell you why it works, right? That should not be something that we then build upon and go forward, right? If I say, look, there's this interesting relationship that I can't explain between, you know, the size of your left index finger and your ability to, you know, do math, right? That's fine. That's an interesting observation, but it should not be published as any kind of causal or any kind of knowledge along that lines, right? What?
What if it's useful for policy, effective policy?
I mean, I don't know if we can use. I don't know if I would argue that we should use it, right?
The classic example here is 1984 or something. Robin Dawes, psychologist, who shows that the simplest linear regression model outperforms the Pennsylvania Parole Board determining recidivism.
Mm-hmm.
So basically, the convicts come before the parole board, and they basically con parole board. And so the counterfactual is you just got to outperform the parole board. A linear regression model. Did the guy make a shiv in the workroom? Has he gotten in a fight? That simple linear model radically outperforms the parole board.
No, it's interesting because I've heard some stuff since then that shows that a lot of those algorithms actually fail in exactly some of the same ways with regards to race, right? That the predpol policy fails, where it overpredicts that a black inmate will, I don't know what we call it, recidivize, right? And a white inmate won't. And it's reverse when you actually look at the data.
But if the counterfactual is the parole board, and I'm sure there have been many parole boards that have been race biased also.
Yeah. No. And in fact, in this particular case, I feel like the answer is to update the algorithms, right, and to update the status. But again, they should be mechanistic algorithms that are openly interpretable. A linear regression model, I would argue, is fairly linearly interpretable. I don't think I would argue that we can't use the linear regression model for policy. I am not arguing in any way that we should not be using algorithms for policy, right? I'm arguing that those algorithms that we use for policy should have clear theoretical explanations as to why they work, right?
One term of the regression has no obvious theoretical interpretation.
Right. But we can take the regression and I'm not arguing for historically existing theory, just that there is a theoretical argument that could be made or that could be drawn upon historically existing theory to make that argument. Yeah.
Old debate in economics about structural modeling.
Yeah.
Econometric side, and Rob's, I mean, the case, the AR model for when you've got clear exogeneity, so an AR model for weather forecasting versus the big models, if it's doing okay, that'd be interesting because you've got clear exogeneity. Once you have all sorts of potential endogeneity in there, then you kick over to we're just as structural models as DSG models in economics. It's the same debate, and so we need I mean, I think what we're doing. I think we approach it, and we'll approach it in different ways.
Yep.
I mean, the generative system stuff is going to be one.
Yeah.
Other, as you know, big data. We need to generate our own data.
Yeah, and
are you getting to that? So like we can.
Well, yeah, I'm gonna end just quickly by showing a couple of quick examples of ways we've actually made this possible. And I think some of it gets to what you're talking about, Rob, which is that some of our approaches do not generate a theory that is we don't know the theory. We just put theoretical constructs in that we know could result, and we then look back at it, and we may have to reinterpret the theory, right? We may have to look as to what is going on. I mean, I don't think any of us in here are arguing that, generative social science essentially was, here's a theory, I'm going to build a model of it and go forward. I think inverse generative social science is about the fact that we put theoretical constructs into the system, allow them to be mixed and matched and played around with in a whole bunch of different ways, and then we get essentially a new theory out of it, right? I am not reserving theory in this way, the way that a lot of my colleagues do in the business school, which means that there's been 20 papers already written about that topic, right? I'm reserving it for the fact that we can tie to objects that we know in maybe 20 papers, but the exact formulation might be completely different than any of those 20 papers discussed in the past.
Mechanism, you're okay with substituting mechanism for theory?
Yeah. Okay. So I'm going to take it from point of view of data-driven agent-based modeling. I hope you all can kind of agree with that as we move forward. All right, why am I not getting the next slide? Okay. And for me, and I kind of want to just give my, Josh mentioned this quickly at the beginning, and I'm way over time, so I'm just going to kind of quickly try and go through this. But I view that there are kind of two branches of ways to do this. And one is to take a pre-given theory, but we might not know the exact parameters of that theory, right? And then do parameter optimization to the empirical data that exists, right? And so therefore we have a new theory exposed by the agent-based model, which is essentially the old theory with a bunch of coefficients in it. And that's essentially linear regression to a large extent for agent-based models, right? It's just that we might not use a linear regression algorithm, we might use a whole bunch of other approaches for it, right? And then the other way, which I would argue is, and by the way, we built a tool to do exactly that, Forrest and I did, and mainly Forrest, I just kind of told him what I think he should look at and read. And he built Behavior Search, which is a NetLogo add-on where you basically tell it what parameters it can manipulate in your agent-based model, you give it a function to optimize, and it goes out and optimizes that function for that model, right? And it's very easy to do this in the case where you want to match empirical data. You just write a function that matches the output of the model to empirical data, and so now we clearly have a parameter optimization tool built in. And it uses genetic algorithms, it uses stochastic gradient descent, it uses whatever you want. Yeah, Paul.
I mentioned this briefly yesterday, but I'm going to try to do a better job on it today. Instead of sticking with the data that we have, that has been, observed data, suppose that before you go forward with your result, you bring in people who worry about the biases, about the unintended consequences and so forth, and then you think about, well, can't we predict some really bad consequences and put those in as artificial data and then optimize, and you get a different answer. And wouldn't that be better than optimizing against the existing data that doesn't look forward and doesn't look to the corners? It seems to me that is that's a technique that could be used routinely.
So you would be optimizing against what the experts say they should?
Data supplemented by put in some really bad points that you don't want to have happen, and so you create, you imagine the results for this would be really bad, so put in a data point that says this is a really bad result. So this is obviously a mixture, but it's not as crazy as it sounds, because in most problems, good analysts can figure out ways, the combinations that would be really bad. They've never been observed before. Why shouldn't those predictions, which are not crazy,
you're saying they would also give us the prediction, not just the conditions?
it's like artificial data. It's
Right.
like the military does war games.
Yeah,
So
I
you
got you.
go through war games
We're saying the same.
of things that have never happened. Analysts use scenarios to look at things that haven't happened. Some of them should be taken very seriously. So suppose, for example, that a country has never had, has had lots of battles and wars, but it never suffered a surprise attack. Well, the analysts would say, you know, if there's a surprise attack, we lose. But it's not been observed yet, so it's not in your data. Let's put in an artificial data point that says, but we lose if this happens. Then your resource allocation, the way you prepare your defenses, would be different. So I'm suggesting that some artificial data should be treated on basically an equal basis with historical data when you really believe that under these circumstances, bad things would happen.
Yeah.
I think you're turning that into a classification problem, and what you'd have to do is take your real data, basically label it. And with that, if you wanted to feed something into your real data and say that the consequence was bad versus good, then you would be doing an optimization as well as a classification exercise.
Yeah, I don't know if I'd want to mix those two. Though it'd be interesting. It'd be interesting to play around with. I do think it would be interesting to see how the results might differ between a model that was just trained on the empirical data and a model that was trained on and see if there were vast differences in the model, right? Yeah, if there's no difference, then, then that's fine.
Generative social science. What are you learning from the data, the counterfactual data? If you're learning how not to generate that, is that what you wanted to find out? Or you're learning if the system that you think exists could possibly generate this?
Right.
Well, it could possibly sound like more skeptical. I think the reason that scenario work and all sorts of projecting ahead, including the anticipate what the bad guy is going to do after we do this, all of those things have actually a really solid basis in past experience.
Yeah.
But in social science, where people love data, whether it's good data or bad data, they love data. This other kind of information, I think, is at least equally important. Now, it depends on the case. And if it didn't make any difference, that would be great. I give you another example. That's a nice example that in the aircraft business, where Boeing will develop a next aircraft, and its engineers develop detailed models of everything, but there's this embarrassing thing that when you look at really stupid models that are called empirical models, the cost that they should charge for the airplane is twice as much as the engineer said. What's the CEO going to do? He's going to hedge because, empirically, you have reason to believe that the engineers don't have everything yet. So there's value to empirical data, even though you don't understand why is it coming out that way. Mm-hmm. But the engineers are also saying, well, you really should train the pilots if you're going to put in this new system, or you might have accidents. That's something where, the theory, the engineers, told us something that Boeing in that case chose to ignore to their detriment and everybody else's. So it's not one or the other. You're using...
the other comment I would make on this is that, in fact, it's funny you mentioned these extreme cases and these, we actually talk a little bit about this in the paper I wrote with Roland on agent-based modeling for marketing, of all things, because we talk about how to do agent-based modeling rigorously, and we talk about a verification phase and a validation phase. And part of the verification phase that we actually discuss is making sure that if subject matter experts say that these are the inputs and this is the output, that your model can't account for those, right? So I almost view that as not validation, which is comparing the agent-based model to the real world, but verification, which is making sure that the mental model that you have, which hopefully is informed by these experts, right, matches the actual implemented model that you've created, right? But it is interesting to me to think about the fact that obviously you can't get every subject matter expert every time when you're constructing the model, and it'd be interesting to bring them in as an additional validation point or an optimization point later on. I think that's an interesting idea. Let me talk about the other approach that we have, right? which I actually was the one I was going to talk about for most of this talk, and I'm going to wrap up in 5 minutes and just at least briefly mention it. But rule induction, right, which, I think a lot of the approaches that we've seen are in this space, right, whether that be Chataka's EDM work, right, or EMD. I just want to call it electronic dance music instead. Or whatever is kind of in this space, right? And there's been past work in this, but it's been kind of the minority of what's been done in agent-based modeling. If there's comparison to empirical data, it's usually over here in most agent-based modeling. It's not over here. There have been some examples where this has been done. I actually was part of a dissertation in 2011 by Yandin Liu, where she just gave rules to all her agents deciding on commuter choice in the Chicago area based upon a Chicago area study of where everybody lives and what patterns they use to get to work. And so she inferred rules of behavior of how people get to work based upon demographic data that she had extracted from that Chicago area study, right? And she used associative rules, like cars, essentially, right, for that. But you could use decision trees, you could use random forests, you could use anything along those lines, right? What I was going to talk about briefly that we've done, we already kind of talked through this, so I'm just going to skip it. That's I actually did write a paper similar to what Sander was talking about with Forrest, where we kind of formalized the parameter optimization process and talked about what was going on there, right? You have this model and you have the real world and you have a set of parameters you're calibrating, right? And then you divide your real world data into training and testing and you compute what's going on. And I'd be happy to chat about that. The interesting result we had was that one thing that's parameter optimization is very sensitive to is how you compute your error function. If you compute your error, if you use root mean squared error to compare your output data to real world data, then your model will be very fit to root mean squared error. And if you do correlation, then you'll be very fit to correlation. And so we couldn't find a single, we were looking for the one ring to rule them all, and we couldn't find it, right? There is no error function that Pareto dominates all the other error functions, right? It's really has depended upon what you're looking for. And so we make the argument in the paper that you need to think about that and think about what kind of errors you want in your model in order to look at that. We use this for doing things like studying urgent diffusion. These are Twitter networks of Hurricane Sandy and Hurricane Irene, and tried to figure out what the best model for people deciding what to do and how to pass on information in that space was. And we were able to create, much like those Kriging maps that Sander was showing, very similar. These are essentially 3D maps, but I only plot them in 2D because it prints better that way, right? Of the sensitivity of the model to a variety of parameters, and we can identify the best parameters that are in that space, right? And that's all parameter optimization, right? So rule induction, right, is instead of focusing on how to adjust a known model's parameters to the data, we're going to take the data and try and infer rules of behavior for the agents, the individuals in that data, directly from the data, right? And I gave the example of Yandin Liu's work that's in that space. Chataka just showed a bunch of examples in that space. But we actually used something different. We actually built on some work that Jim Crutchfield and Cosma Shalizi did, who at the Santa Fe Institute a long time ago, but they're still working on that, called causal state modeling. And what causal state modeling allows us to do, and by the way, it has a bunch of names. It's sometimes called epsilon machines. It's sometimes called computational mechanics, right? What causal state modeling does is give you the ability to take any time series data that you have whatsoever and infer a model of the behavior of that time series that is Markov-like. It's not actually a Markov model for a variety of formal reasons, but it has similarities to Markov models, right? And the nice thing about this is that because Cosma is such a smart statistician, he was able to prove I think it's in his dissertation actually, that that these machines, if you use this causal state splitting and reconstruction algorithm that they developed, are maximally predictive. In other words, they do the best job of predicting that you could possibly do given the training data that you have, right? And minimally complex, i.e. they have the fewest number of states that you could possibly have for the system, right? And that's not true in theory, that's true in practice, that Cosmo is able to show that for any particular training data set that you give it, it is true for that data set, right? Which is a kind of a nice little takeaway. So what do we do with this? Well, we took this and we built a model to just simply predict whether or not someone's going to tweet in the next 10 minutes, given their last 2 hours of Twitter, hour and 40 minutes of Twitter activity, right? And what we found was that we didn't do very well at predicting people who never tweet, sorry, we did do very well at predicting people who never tweet. We just didn't do very well compared to the baseline models, right? And I'll tell you what those are in a second. And we didn't do very well for people who always tweet, right? Because these are both easy to predict people, right? It's very easy to predict if someone's always tweeting, whether or not they're going to tweet. It's very easy to predict if they're never tweeting, that they're never going to tweet, right? And the baseline model, I should explain for the comparison here, is to a model where you just take a majority vote of the last 140 minutes. Did they tweet more often than they didn't tweet in the last 140 minutes? Did they tweet less often than they didn't tweet? And that's the baseline model. So anything above 0 indicates we're doing better than that model. Anything below 0 says we're doing worse. The blue dots are for that causal state model that I explored. One of the things we did here is we did compare to a black box model. We compared to an echo state network, which is essentially a recurrent neural network with random wirings between the internal connections and trained weights on the inputs and outputs, right? And what we wanted to show was we're at least as good as the black box model. We can get the same results, but we at least have what, and this is where I'd get into, a potentially theoretically interpretable result, right? And what I mean by that is we get an output. It's based upon patterns of behavior that we know that people move between these different states of behavior when deciding to tweet or not, but it doesn't have a theory attached to it automatically. You have to go in and attach that theory to what is the output of that, right? And we were able to do really well, right? That's the basic example.
Can I just say this? Let me just interject here right now.
Yeah.
Mentioning that I find this disconcerting in your presentation because the Shalizi Kurzweil thing is the ultimate black box. It's in fact the minimal size black box that explains the data.
Yeah.
So in fact, it goes against what you said at the start. And
I don't know if I agree with that, right? And here's why, right? I can actually, so here's another example, right? But it turns out that the vast majority of that Twitter example are either 2, 3, or 4 states. That's it, right? And so we know exactly, there are labels of behavior that people have theorized in this space. That, for instance, people are more likely to tweet when they're at their desktops than not at their desktops, right?
But you're just implicitly, everybody's homogeneous. The same rules apply to everybody.
No, we are actually learning different rules for everybody in this one. Everyone has their own rule.
Okay.
Yeah, but Bill, I think the crux of the matter here is that what type of data you have, right? If I have a football field and the only data is the sound of the football field on something event that is happening that I don't know who's playing, what they're doing. I just hear the sound, and the volume of the sound is my data. I could get one of those machines to predict something like that, but it will make sense. I mean, it's like
You're absolutely right. Like the approach that I'm not arguing we should use causal state modeling for every single data set out there.
Yeah.
There's a very specific set of data sets it works for.
There is almost like your data has to have some sort of causal relationship. It's almost like
right. And
what type of data?
I mean, that's exactly my answer to Rob. We had an explanation for this. Like we didn't go in there and just like randomly throw something at a random set of data. We knew that people's behavior tended to be bursty in this space. There's a ton of literature on that. We knew that there was behavior governed by the way they interact with different devices, but we didn't have access to that, so we had to model it by proxy.
But the thing is that I don't think we have a formal way to classify the data towards the model and say, this is data type A, so this will make sense.
No, we do for causal state. Like we know what kind of data causal state modeling works well for, right? It works well for high frequency, low alphabet type data, right? So where we don't have a lot of states going in and we have a lot of individual level data. We could create a separate set of those rules. I'm arguing that we should, in fact, as inverse generative social science, right, create a separate set of those rules for GP type data, GP type approaches, for random forest type approaches, for whatever else we're going to use in this space. Mm-hmm. Right? I think we can do that. I think that's our research agenda, right? But I think it's possible.
But the mere fact that it's minimal is still rubbing the wrong way, because human behavior is not necessarily, rational, minimal, optimal, anything like that, right? So
you might be right, Rob. maybe like, I guess I am not so tied to causal state modeling, right, as I am tied to something that gives us an output that we can look at and somehow interpret, right? The recurrent neural net is the opposite of that interpretation, right? In the recurrent neural net, right, we have to, like, there's a bunch of random wirings in the middle of it that we don't know why they're wired to each other. In fact, they're specifically set up so we don't know why they're wired to each other, right? Now, we can do explainable AI where we pass inputs through and get outputs and start to draw a relationship. But here, we don't have to worry about that. We can actually follow the thread of any input into the system and figure out what's coming out the other end, right? And maybe this is not the most mechanistic model you could possibly generate. I like the fact that it's minimal, right, because of the fact that it's giving us the smallest model that we need to account for the data we've observed, right? Which kind of gets back to, like, the Tom argument that you were talking about earlier, right? That it's as small. We've taken away as much as we possibly can from the system. Right? Yeah. If in fact, like, there was some important thing that we needed to account for, and in fact, it is. Like, let me give you a great example. This is actually, so this model, I think, is a very good model for individual time series predictions when you're interested in what's going to happen in the near future. That model fails horribly when you're talking about what's the Twitter spike, how many tweets are there going to be a week from now, right? Because it doesn't take into account seasonality, which is an important aspect. Now, we built another model that had a clock in it, right, as one of the transducer inputs to the causal state model, and that model works much better at predicting the spikes out on Thursday, right? So in fact, this model did violate exactly that assumption. And I mean, I'm not tied to any of these particular mechanistic approaches. In fact, I'm no longer using causal state modeling. We've moved to sparse Markov models for a lot of the work that we're doing. But it's an example I thought of that I thought was.
Yeah, but Bill, I was just wondering. I have kind of like a theoretical question here. So, and the question is, like, why bother about mechanistic models? So, I'm coming from very practical, applied side of research, and so what I could see here, from your explanation of what you're doing, you don't care why people are tweeting. So what you want to do is you want to make prediction.
Yeah.
If you want to make prediction, why would you bother about all this causal explanation, like, and people can have, like, different reasons for doing that. If I'm talking about policy, that's where I really want to understand causality. I really want to understand, how to do that, because that's
we do
where
care
I need
about
to
that.
have.
I'll get to that in a second.
Yeah. But
yeah,
here, if I was
you're exactly right. You're exactly right. We built this model first to show that we could actually do it and we could get good predictive results because we didn't know if we could or not, right? But what we really want to know is if I were to send out a tweet at this particular time, right, how many people are likely to be online and able to receive it, right? And I can use this model to kind of infer that essentially from the data that I've seen, right? And I can see exactly which users, because they're at the individual level, right? I'm learning every agent has its own model. I can say that this segment is more likely to be online at this time than this segment is, right? And let me give you another example. This one, unfortunately, wasn't at the individual level, but that's because we didn't have the data yet at that level. We could have run it at that level. This is marketing attribution, right? And so this is exactly the problem you're talking about. I want to understand what causes, this is from, it's from a hotelier in the area who's big and owns lots of worldwide chains. But we have data about all the promotional activities they did, and we knew whether or not someone booked a hotel on their website, right? That's what we knew. And we had data about paid search, email marketing, display advertising on blogs, whether or not you got a mobile pop-up display on your phone, right? Every possible channel that they could communicate with their loyal customers, their loyalty customers, right? And we wanted more data because we think we could divide this, but at the time, they only gave us like a month's worth of data, so we didn't have enough, right? Well, what we were able to do, and I don't have time to talk about this, but basically we were able to figure out what state each person was in the kind of standard consumer search funnel theory of like I'm exploring everything versus I've decided this area versus I'm making a purchase. And we figured out which intervention would have the highest probability of resulting in them making a purchase in the near future, right, from that website. So exactly the point you're making, if we had used the black box model, where we just predicted based upon inputs whether or not someone was making a prediction, we wouldn't have gotten this nice map that kind of folds up nicely with consumer funnel theory as to how people make searches, and we wouldn't have been able to make those interventions, right? So even though it is minimal state, right, it gives us insights into what we're doing. And you're absolutely right, Rob, there might be other alternative forms of doing this that might be less obtuse, right, less black box, and might give us more explanation, but this one worked fairly well for at least a couple of projects we tried it on. With that, I should probably really wrap up, but I think we've had an exciting discussion. I do want to leave you with one thing. I have this vision, right, of inverse generative social science, which is that we could, if we can truly model individual users well, automatically, and we could potentially embed these models into a full simulation of whatever system we're starting. So the example I pitched to NSF a couple of years and never got funding for it was, imagine that you were a city government and you had full access to all the administration for that city, and you had access to be able to collect all the social media data you wanted about that city and all the interesting insights. Could you build an agent-based model of that city that was modeling individual level behavior in near real time, whether it's real time or not, right? And could help you address questions like, what happens if I close down this street? What happens if I put in a tax on garbage, right? What happens if I do these kind of different questions, right? And I feel like inverse generative social science is one path, or probably maybe the only path, to really get us to that kind of a vision, right, where we could build these big scale simulations that look like that. This policy flight simulator that John Howland and John Sturman saw. So with that, I'm going to end my part. I probably don't have much time for questions, but we can, if there are any left, I'll take one or two real quick.